The ideal gas law. By definition, an ideal gas is a hypothetical gas whose pressure, volume, temperature, and temperature behavior can be completely accounted for by the ideal gas equation. In other words, we're going to assume that it's actually following the kinetic theory of gases exactly. And we're going to get to the kinetic theory of gases. The molecules of ideal gas do not attract nor repel one another. That's actually one of the concepts from the kinetic theory of gases. They don't attract nor repel one another. And we're so used to attracting or repulsion, where we've been dealing with these electronegativity, these actual chemical bonding, going back and understand forming a chemical bond. They have to attract each other, or we're drawing these Lewis structures, or we understand there's repulsions actually occurring here. That's not between gases. Next, another thing is that the volume of molecules in an ideal gas are negligible. These gas molecules are so very, very small, again, their volume is just, again, there's a volume, but it's so small it's just negligible. All four of the variables, the same four variables we just talked about with our gas laws, now we're going to bring them all four into play. So now the mole comes into the picture and the mole becomes active. Here's a term, law of combining volumes, and we're going to bring this back into play because the roadmap's coming back into play. And what the law of combining volume says, the volume of a gas that react with another at the same temperature and pressure, so we're assuming temperature and pressure are the same, are in a ratio of coefficients of the balanced chemical equation, the mole-to-mole ratio. So what we're going to see here, if I have my balanced chemical equation, 2 moles of hydrogen plus 1 mole of oxygen will produce 2 moles of water. It's a 2 to 1 to 2 ratio, mole to mole to mole. It's also a 2 liters of hydrogen and a 1 liter to every 1 liter of oxygen to every 2 liters of water. So volumes can be, this is going to be a shortcut. We're going to bypass the mole to mole ratio and literally go from one side, one volume of a gas to another volume of a gas by setting up now a liter to liter ratio, yes, still using the coefficients in balanced chemical equation. We're going to come back to this with when we bring up the roadmap back into play. But remember, in order for this to occur, temperature and pressure must, again, in this situation, remain the same. Avogadro's hypothesis. Avogadro's hypothesis says equal volumes of gas at the same temperature and pressure contain the same number of molecules. In other words, their volume is negligible. If I have these two gases, I'm going to do my two normal gases. I have helium and krypton, and I'm going to say both of them are 5 liters. I have the same volume. Both of them at a constant pressure. And both of them, again, even at a constant temperature here. So I have the same volume container, both same pressure, same temperature. If I had in a box, if I could get 3 heliums in there, I could also have 3 kryptons. Again, in this situation, what we're saying is the size of the molecules, or the same number of molecules, or the size of the gas, actually in this situation doesn't actually matter. Again, remember the volume of the gas is actually negligible. They're so small, it's just, it's usually it could be like, well, we have a Volkswagen out front, and we have how many seniors can get in that Volkswagen versus how many freshmen can get in that Volkswagen. So it's still the same Volkswagen, but yeah, the freshman size actually does make an impact here because your freshmen can be smaller, so you're going to get a lot of little freshmen in that Volkswagen versus very few seniors because they're so large. For gases, this isn't even an issue because, again, their volume is so small. Avogadro's law. Avogadro's law brings in another constant for us, and it says at constant temperature and pressure, again, we're dealing with this constant temperature and pressure, it says volume of a gas is directly proportional to a mole. Just like pressure is directly proportional to temperature, volume is directly proportional to temperature. Now we're saying volume is directly proportional to a mole. So what this means is volume divided by moles equals K, so it always equals a constant. And so again, they have a direct relationship. This will come into play with the ideal gas law, so you want to remember this concept, very, very important. But this also brings in another conversion factor, and this conversion factor is called molar volume. We have molar mass, we now have molar volume. Well, at STP, you can use this molar volume, and the key is you have to be at STP to be able to use this, and the problem has to tell you STP. You cannot assume STP. I must tell you that in the problem. But if I tell you the problem is at STP, Just like molar mass, we know 1 mole of mass equals certain mass we have on the periodic table. Well, 1 mole of a gas will equal 22.4 liters. 1 mole of a gas will equal 22.4 liters. That's a constant. So kind of using this this molar volume at STP, I give you a problem. I said determine the number of moles of helium gas in a 5-liter container at STP. Well, you're starting out with a 5-liter container. Well, you know that for every 22.4 liters of helium, there's every 1 mole of gas. There's your conversion factor, and it actually comes into play. And you can see what this conversion factor helps you get from volume to moles very, very easy. And this is very, very helpful back in the roadmap, because commonly a lot of times we have to get back to the mole. So molar mass helps us get back to the mole. We know that 1 mole is equal to 6.22 times 23 to the 23rd molecules. Helps us get back to the mole. So this is just another way to get back to the mole. So our liters cancel out, so just multiply across and divide. So really all you're doing is 5 divided by 22.4, 3 sig figs and 5 liters, therefore 3 sig figs in your answers, you need moles of helium. Now let me take it a step further, dealing with the roadmap still. Now I want to calculate the mass of oxygen. This again, we say, well, we have 14.4 liters of oxygen gas. What is its mass? Well, knowing going back to the roadmap, we know that the end of a mass, I can use molar mass, but I have to get grams per mole, I have to get back to the mole. Well, how can I get there? Well, I know that in 22.4 liters of my oxygen gas of any gas is equal to 1 mole of that gas. That's a conversion factor at STP. So my liters cancel out, now I'm in moles. Well, then I know that 1 mole equals the mass of oxygen, which is 32.00 grams. My moles cancel out and end up in grams of oxygen. So let's multiply across. 14.5 times 32 divided by 22.4 equals, for 3 sig figs, you're 14.5, therefore 3 sig figs in your answer. That gives you the grams of oxygen. So that conversion factor becomes very, very helpful. It's going to get us back to the roadmap. As we continue on, we will get there. Let's talk about this ideal gas law, though. Now, taking all of our gas laws we dealt with, we had actually Boyle's law, we had Gay-Lussac's law, we had Charles' law, and we just had a new one, we had Avogadro's law. And all of these are equal to K. As we look at this, we have the P and the V in the numerator, and again your moles and temperature in the denominator. And so all of them are equal to the constant K. We're just going to change K to R. Okay, representing, so it's just it's still a constant, but we're just going to change it to R. And so now we see, well, PV divided by NT equals R. Well, we make it linear. PV equals nRT. There's your ideal gas law. Circle it. You're going to use it over and over again, quite often here. And so in this situation, we see we have our pressure, we have our volume, we have our moles, we have our temperature. Well, we're going to have a constant, and that constant is R. Well, let's now solve for R. We can actually go back and solve for R. And so using our equation, PV divided by NT equals R, we can actually plug those in. So what's N? Okay, N is standard N, temperature for N is 1 mole. Standard volume is 22.4 liters. Standard pressure is 1 atm, and standard temperature is 273.15. So I just plug them in, my pressure and times my volume divided by my moles times my Kelvin. Now, as you see here, unlike what's happened with all the maths, with all the other problems, the units do not cancel out. They stay intact. And so what happens, that's important because that develops the units for your R. Your numerical value for R is 0.0821. The units are liters times atm divided by moles times Kelvin. And what's important about this, these now units in your R govern your pressure, your volume, your moles, and your temperature. Pressure now just can't be consistent in psi, kilopascals. It now has to be in atm. Your volume cannot be in milliliters, centimeters cubed, or anything like that. It has to now be in liters. Your moles, yes, moles just have to be in moles, and temperature does not change. Temperature has to be in Kelvin. Now your N is your amount. Now commonly what I will give you your amount, I love to give you your amount not in moles, but I love to give it to you in grams. But the fact is you can't plug grams into this equation, you must plug moles, so you have to use good old molar mass to get back from mass to moles. So you can kind of see there's going to be a lot of busy work now with these ideal gas problems because you have to adjust all the units so they match up with R. So let's go through and practice this. Just remember the units for R. Liters times atm divided by moles times Kelvin. And remember temperature must always be in Kelvin. So here's our problem. Calculate the volume of 16.0 grams of oxygen gas at 100 degrees Celsius and 155 torr. Now there's a couple of things I see different here. The first thing, which is the most important thing you have to see here, and you know you're not using your regular gas laws like Gay-Lussac's, Boyle's law, the combined gas law. I'm not worried about those because now I've been given an amount. Once I gave you an amount, remember none of those earlier gas laws, Boyle's law, Charles' law, Gay-Lussac's law, combined gas law, none of them gave you an amount. Mole was not present in the picture. So that points you right away to the ideal gas law. The other issue is with my temperature and pressure, there's not an initial and a final. There's one temperature and there's one pressure. That also points you to the ideal gas law. So in this situation, we first realize my amount. My amount is my N. My problem is my amount is in 16 grams. It can't be in grams, it has to be in moles, so I must use good old molar mass. I get that from the periodic table. And so in this situation, I go to oxygen. Oxygen weighs in at 32.0, sorry, but there should be a second zero in there, so 32.00 grams per mole. And so my grams cancel out, and I simply just divide here. So 16 divided by 32 equals, again, maintaining my 3 sig figs, is 0.500 moles of oxygen. That's my N. The next piece of information I have here is I have temperature. Well, temperature, my problem is in Celsius. It must be in Kelvin. It's 100.0, has one digit to divide by decimal, so my 0.15, and my 273.15, the 0.15 rounds up to 0.2. So I just ends up being 330 or 373.2 Kelvin. 4 sig figs in that, by the way. I go now to my torr, and now I realize that I just can't be consistent. I have to be in HChem. So I have to use my conversion factors I gave you back into play. They're going to come into play now. So I know that 1 HChem is equal to 760 torr. So I set this up. Basically, it's divided by 760 torr. Or by divided by 760, I end up with 0.2039. I left out 4 sig figs. Ultimately, does it matter here? No, it doesn't. Because when I look at sig figs, I always go back to my original value. For my amount, I will look at grams as 3 sig figs. For my torr, my pressure, I will look at 155 torr, 3 sig figs. Temperature, however, I must look at Kelvin, and that's 373.24 sig figs. These sig figs are 3. My answer is going to have 3 sig figs. So this is a lot of busy work. Now we can finally get to the problem. We do know R. We can finally get to the problem. We're solving for volume. So now I take my ideal gas law, do a little bit of pre-algebra. I want to isolate my volume, so I divide both sides by pressure. So it's nRT divided by P. I plug in my N, I plug in my R, plug in my temperature, and divide by my pressure. Now, all the units have been matched up here with my R, so they do cancel out. My moles are going to cancel out. My Kelvin are going to cancel out, and my ATM are going to cancel out, and I'm going to end up in a volume of liters at 75.1 liters, 3 sig figs. Here's another problem. What pressure will 35.5 grams of carbon monoxide gas exert if it is in a 15.5 liter container at 20 degrees Celsius? Again, I have an amount, so the ideal gas law. Again, my amount is in 35.5 grams. It must be in moles. So I look up carbon monoxide. CO, little nomenclature came into play again there. If you don't know the formula for carbon monoxide, and you mess up on molar mass, and you mess up on moles. So no, your molar mass, your nomenclature again. So I add up 1 carbon and 1 oxygen, weighs in at 28.01 grams per every 1 mole. I simply divide, so 35 divided by 28.01, and I'm going to have my grams cancel out, and I end up with 1.267. Again, I'm not worried about sig figs right now because I know my original, always go back to my original values. At 35.5 is telling me there's 3 sig figs according to my mass. My temperature. My temperature comes in at 20 degrees Celsius, 20.0 degrees Celsius, 1 digit to the right of a decimal, so again it's going to be a 0.2, so again at 293.2 Kelvin. 4 sig figs there, by the way. Then I have my volume. Volume is in 15.5 liters. It is in liters. That's what my R is already in liters. I don't have to do anything with it. There's 3 sig figs. So look at my units in, okay, my units are going to have 3 sig figs. Or my answer will have 3 sig figs. There's my R. What am I solving for? Now I'm solving for pressure. So there's my ideal gas law. Again, a simple pre-algebra again. Now you want to isolate P, so you divide both sides by V. And again, now pressure equals nRT divided by volume. You already have the units set up perfectly, so you just simply plug them in. Now your moles are going to cancel out. your Kelvin are going to cancel out, and your liters are going to cancel out. And you're going to end up in ATM with 3 sig figs. Your answer is 1.97 ATM. Next problem. A vacuum pump removes the air from a 4.5 liter bell jar. If the final pressure of the bell jar is 0.000185 atm, how many air molecules remain in the jar? And the temperature is at 20 degrees Celsius. So again, what do we know? I realize again I'm in a volume of 4.5 liters. I have a ATM of 0.000185 atm. And I have a temperature of 20 degrees Celsius. So right now, both my original values, I'm looking at 3 sig figs. My 20 degrees Celsius has to get up to Kelvin, so I add, it's maybe a 0.2 again, but there's 4 sig figs at 293.2 Kelvin. The nice thing is my volume, pressure, and temperature are all now in the correct units. So I also have R. R is available for me. Now what am I going after? I'm going after my amount. I'm going after moles, but then because I've always been going after molecules, but to get to molecules, I have to first get to moles. Once I get the moles, I can get back out the molecules using Avogadro's number. So again, I look at my ideal gas law. Now I'm going to isolate N. So I isolate N on both sides, divide both sides by RT. I plug in my variables. Plug my pressure and my volume, and my R and my Kelvin, and temperature, and everything cancels out. ATM cancels out again, liters cancel out again, my Kelvins cancel out, and I end up being in moles because I'm in that multiplied by my reciprocal anyway, because my units are in a fraction in the denominator. So I end up in moles. But this is not my final answer. I don't want to know moles, I want to know molecules. So I left it drawn out here. I wasn't going to round up and lose significance because it wasn't my final answer. So now I take my moles, 3.458 times 10 to the negative fifth moles, and I know that 1 mole is equal to 6.022 times 10 to the 23rd of anything. In this situation, my anything are molecules, so I simply multiply across. 3 sig figs, the answer ended up being 2.08 times 10 to the 19 molecules. Fourth problem, it says determine the pressure of a gas in psi. In a 125 liter gas cylinder and 325 grams of oxygen gas at 22 degrees Celsius. Now I want to get out the psi. My thing is, though, with my ideal gas law, I must first solve in ATM. Then I use my conversion factor. I know that 1 ATM is the same as 14.7 psi. Good job. And so then that can get me back out the psi. But first of all, I must again identify what I know. I know my volume is 125 liters. Liters are in the correct unit. I'm set. Secondly, I know my amount is 325 grams. Not in the correct unit, it must be in moles, so once again use molar mass. Oxygen weighs in at 32.00 grams per mole. Simply divide, and I end up with my moles of oxygen. Again, I'm not worried about sig figs at this point in time, because I know my 325 initially had 3 sig figs. My 125 volume has 3 sig figs, so I'm looking at 3 sig figs right now. The next piece of information I know my temperature at 22 degrees Celsius. Now there's no digits to arrive at decimal, therefore I'm just adding 273, so it's just plain simple 295 Kelvin. 3 sig figs in my Kelvin. So right now my answer is going to have 3 sig figs. What else do I know? Well, you know R. R is a constant provided for you, and you identify what you're solving for, so you're solving for pressure. Here's your gas law. Again, you want to isolate pressure, so you divide both sides by volume. In this situation, you plug in the values. Your moles are going to cancel out, your Kelvin are going to cancel out, your liters are going to cancel out, and you end up in ATM as expected because you're going after pressure. But once again, my ATM are not my final unit. I want to get over the PSI. So I know my conversion factor is that 1 ATM is the same as 14.7 PSI. So it's 14.7 over 1 ATM, so you're just going to multiply, and you end up with 28.9 PSI, 3 sig figs.